In this video, I'm going to talk about exception handling in Python and how it works. I'm also going to show you two advanced mechanisms that help you improve the way your code handles errors. If you're new here and you want to become a better software developer, gain a deeper understanding of programming in general, start now by subscribing and hitting the bell so you don't miss anything. An error condition or error is traditionally viewed as a condition that occurs during runtime that can't be handled by the normal flow of execution of a program. It's not a bug because it's not something that you can fix in the code. For example, a file that can't be found, some device that you're expecting to be connected is not, internet connection is lost, an authentication token is no longer valid, etc. Most programming languages make a distinction between syntax errors that happen during compile-interpret time and other errors happening during runtime. In Python, that difference is less clear because parts of the program may be interpreted only when they're needed, and handling errors while interpreting or errors while running the program are both done using exceptions. This means that in Python there's more or less no way around it. If you want to properly handle errors in your Python program, you have to do it the Python way. And that means exceptions, whether you like it or not. Exception handling is a pretty old technique. It was first added to the Lisp language in the 1960s. Nowadays, exceptions are a common pattern in many languages, and it's considered the standard way of dealing with errors. It's not without criticism though, and I'll talk about that later on. But let's first look at a couple of examples of handling exceptions in Python. I thought it'd be nice to do an example about an API. So I used the Flask platform in this case to create a simple API for accessing blog posts. Here we have the Flask application. It's very basic. There is a hello world, which is just there for testing the Flask basic route. There is the blogs route, which fetches blogs from a database, and there's a route that fetches a specific blog given some ID. Each of these routes calls a function from another file that's responsible for actually retrieving the data from the database. And then before sending it back to the client, I'm calling the JSONify function, which is a function from Flask that allows me to turn the data that I get from the database into a JSON format so that you can retrieve it with an HTTP request. As a basis for the application, I created a very simple SQLite database that contains just one table, blogs, that has a few things like an ID, which is the primary key. There is a date that the blog was published, there is a title, there is some content, and there's also an integer, actually kind of a boolean in SQL land, that indicates whether the blog is supposed to be public or not. And then what I did was just insert a few rows of data into this SQL database. And you can see there's actually a file here, application.db, that contains the actual data in this case. This is the file that contains the actual functions that retrieve the data from the database. So there is a fetch blogs function that simply returns all the blogs from the database, but only the public ones. So that's what this SQL query does. When it retrieves the data, it then converts that data to a dictionary. So that's actually what's happening here. So what you get is actually an array of values, which is each of the columns in the query result. But I want to convert it into a dictionary like so I can send back the data as a JSON object, which makes a lot more sense. Similarly, fetch blog gets an ID and then retrieves the blog with that particular ID from the database. And when you look back at the actual API definition, you see it simply calls these functions. Now obviously you could put the code that is inside these functions directly into the API routes. And for very basic, simple applications, that's perfectly fine. But as soon as your applications become a bit more complex, you kind of want to separate these things. In my company, for example, this is in particular useful because we want to have both a GraphQL interface to our backend as well as a REST interface which our clients are using. So what we did is that we separated the logic of what the backend should do from the actual routing and the interface to the client, which is either an HTTP REST-like request or a GraphQL system. Let's start up the server and see how it works. And this is the Hello World API route that we have here. Now I can also retrieve the blogs. And now you see we get back an array with data about blogs. In this case, there's just a single blog. What I also can do is retrieve a blog with an ID. So let's retrieve the blog with this ID. So there you see, we've created a very simple API that retrieves data from a database. The problem is I don't check anything. So for example, if I write here an ID that doesn't exist, I get an internal server error. You want to avoid that your clients see these kind of errors because they're not very informative. It would be much better to give a 404 or something like that. So let's improve this, and the way to do it is to think about error handling and exceptions. Let's take a look again at these database functions. What we're doing is we're connecting to the database, we're executing a query, we're fetching data from that query, turning it into a dictionary, and then closing the database and returning the result again. That's for fetching all the blocks. For fetching a particular block, it's very similar. Also, database connection, execute a query, we get the results, convert it to data that we want to have, and then we return that data. But here, obviously, things can go wrong. For example, there might be a problem with the connection. Maybe the file doesn't exist. There might be a problem that we didn't find any block here, or there might be any other kind of issue that might occur. SQLite has different kinds of exceptions that it can raise. In fact, Python has a whole hierarchy of exceptions. The main exception class is called exception, and basically every exception should be a subclass of that main superclass. And lots of libraries and platforms provide their own set of exceptions. So for example, SQLite has an operational error exception that you could handle. The thing is that it's okay to kind of handle these low-level exceptions like SQLite operational error, that's fine. But on the API level, you preferably don't want to be handling those very low-level exceptions, because then the API level needs to know that the database is actually using SQLite. And maybe if we change it later, we don't want to go through all the API routes to fix the error handling so that we use the new library's error handling. So the way you could solve this is that in the fetch block function, you would handle the low-level database errors, and then you could potentially raise new errors that are more suitable to the level above. As a first step, let's add a few custom exception types that we're going to use. And in this case, what can go wrong? It's possible that a block cannot be found, and it's also possible that we're trying to access a block that's not public. So let's add a not found error and a not authorized error. And both of these classes are subclasses of the Python exception class. Let's start with the fetch block function. So now we're not dealing with errors at all, but what we have to do is put this into a try block so that we can handle the errors if they occur. To keep this example simple, let's say for now we're only handling SQLite operation errors. So that means we need to add an except clause to the try block. And if we want to do something with that error, we should also give it a name, such as E or whatever, and then we can print it, for example. And instead of now pushing up this operational error of SQLite to the layer above, we can now raise a new error. And let's say, for simplicity's sake, we're simply converting any operational error that we get into a not found error. The problem here is that this operational error is likely to occur somewhere in this part where we're connecting to the database and we're trying to execute a query. So we potentially opened the database and then it went wrong in the query, but then because of the exception, we're not closing the database anymore. So one thing you could do is copy paste this code to the except part, but Python also has a finally clause that contains code that you should always execute regardless if there's an exception or not. So now, in all cases, the database is closed. What we need to do now is be a bit more precise about the way we handle errors. So here we're fetching the result of the query, and that is potentially none, because it's possible we can't find a block. So we need to handle that case here. So if the result is none, then we're going to raise an error. And this avoids the problem where we're calling this function to convert the result to a dictionary with a result that is none. A second thing we should do is check if we're actually authorized to view this block. And that we can do after we've converted the result to a dictionary. If the block is not public, we should raise a not authorized error. And now we can go a level up and actually handle those errors and send the correct HTTP response that belongs with them. So instead of directly returning the JSON data that we got by fetching the block from the database, we're also going to check for errors here. But here we're going to handle the high-level errors, which is not found error and not authorized error, which I will also need to import. So in case a block is not found, we can use the abort function to send a 404 response back using Flask. And similar for not authorized error, we can send back a 403. And you may want to add more information to these particular messages that you send back if you want to. Let me switch to my browser again. And let's reload this page. So you see we get a not found because this block doesn't exist. This was the block we had in the database, and there is another one, a private block that we're not supposed to access. And then you see we get a 403 back. So here you see how you can use exceptions on multiple levels to make sure the right information is transferred. Often exceptions are being seen as a kind of hidden control flow, which they are, and that's pretty bad. It's important to make sure that you're handling the exceptions at the right layer and not pushing them all the way to the top where you don't know what that low-level thing is. We can do something similar for fetching all the blocks, but then we can actually make it even simpler. Let's say we wrap all the code into a try block again, like this. And then we're going to do exactly the same where closing the database is part of the finally clause. And this actually belongs there. There you go. And now what we can do is simply say, okay, we're going to catch any exception that might occur here. Connection problems, query problems, whatever. Let's print it out so that we know what it is. And then we can send back just the empty array. So if there is any problem here, you will always at least get some kind of result. Potentially this is not exactly what you want. Maybe you want to have more precise control here. So then you could add different kinds of exception handling, or perhaps you want to communicate back to a user that there is a problem with the server. But in this example, because we're dealing with the exception on this level, actually here on the error handling part, we don't need to do anything, because fetch blocks is always going to return some kind of valid result. If you don't like this finally part of exception handling, then Python actually has another option for you, and that's using context managers. Context managers allow you to have a bit more control over what happens when objects are created and when they are destroyed. And you can use that to free up resources at the end, which is very useful in the case of database connections. Python already has a few of these context managers, for example, for opening a file. If you open a file and an exception occurs, then Python makes sure that the file is actually closed if you use the with keyword. So we can use a similar procedure for opening and closing the database. In order to do that, we need to create a context manager object, because SQLite does not have this as a built-in feature. And what you need to do then is create a class that has two methods, enter and leave. And in the enter method you specify what should happen at creation time, and the leave method should specify what happens at destruction time. So let's create a class called SQLite where we're going to handle this. In order to work with the database, we're going to need a file name. So that's what we need to pass in the initializer. And then we can add an enter and exit method. In the enter method, we're going to set up the connection. And in the exit method, we're going to close the connection. And now we can use it with the with keyword. Let's see how that works. For example, in fetch blocks, I could wrap this part into a with block. And then I don't need to do this connection part anymore, because that's what the context manager is going to handle for me. Now obviously we're still going to need a cursor. So what you could do is that the enter method actually returns a cursor object. And what we need to do here in the with part is that we need to add a variable. So now we have the cursor that we can use here inside this with block. And because the context manager is going to handle properly closing the database connection if something happens, we don't need this finally part anymore. Now personally, I don't mind using the finally part in an error handling system, but what I also appreciate about context managers is that you have the creation and destruction of resources in a single place. And that just makes it a bit easier to organize everything in your code. So let's start the server again and see if it still works. And now let's fetch all the blocks and we get an empty list. So actually it didn't work because I forgot to add a few parameters to the exit function. So the exit function should have a type, a value and a traceback parameter. We're not using it here, but it's still needed for it in order to work correctly. Let's try it again. Yes, this is exactly what we were looking for. Before we finish this example, I'd like to show you two more advanced things you can do with exceptions. The first one is a so-called retry decorator. You can imagine when you're dealing with database connections or network connections in general that sometimes it's useful to simply retry something. If something doesn't work the first time, it doesn't mean that it's broken. It's possible that some packet got lost in a network or that there was some other connection error, and perhaps you should just try it again and then maybe it will work. And this is a nice function that I found that actually models this behavior for you. So it creates a decorator that you can wrap around a function that keeps track of a number of tries, puts a delay between them, and if there is an exception, it waits a bit, then tries it again for a number of times. And the way you can use it is like this. So let's say you have a function that's going to fail because the only thing it does is raise an exception, but you can put a retry decorator on top of it where you provide the kind of exception that you should handle inside the retry decorator, and then also how often you should retry this. So when we run this particular example, you'll see that it's going to print out this message where it will retry again and again after the exception is raised. And the way this particular decorator works is that it multiplies the wait time every time an exception occurs. And then after 4 times, it simply gives up. So this is a nice way to add a more advanced exception handling behavior to your code. I put this in the Git repository, by the way, so if you want to use it, you can simply find it there. Another thing you could do with decorators and exceptions is that you can automatically log exceptions. So here you see we have a decorator that wraps also around a function where in case of an exception it's going to create a log and then it's going to log that to a file or whatever you want. And it's going to raise that exception again so you can then properly handle it. And the way you use it is that you have this function. In this case this is going to raise an exception because we're dividing by 0, but I put an exception decorator above it, so it's also going to log this. So if I run this, let's see what happens. So we indeed got this 0 division error, but it's also created a log file, and that's over here. And there you see we have the trace, etc, etc. So this is a way to easily add log files to your application if things go wrong and you don't have to write a lot of boilerplate code for it. So we have these exceptions, problem solved, right? Unfortunately, exceptions are certainly not perfect. The first problem with exceptions is that they introduce a second hidden control flow in your program. And this means it's harder to grasp for programmers what happens in the case of an error. And it might break other things that you're not aware of. And that's the second problem. If you're not careful, exceptions may result in resource leaks in case of an error. Not closing a database connection, for example, or not releasing memory that's in use. A third problem is that exceptions potentially introduce extra coupling, because high-level systems may need to know about low-level exception objects if you don't set it up right. It's also not always clear what the error values are. You have exception objects, but those may contain different data depending on the type of error, and you need to document that. And finally, you're never quite sure that your code handles all exceptions properly. And this is very hard to test because exceptions can basically come from anywhere. There are a few other ways of dealing with errors, but they each have their own set of problems. First thing you could do is just terminate the program. Too bad for the users. You shouldn't have pressed that button, you shouldn't have opened that file. Let's not even talk about that solution. A second thing you could do is that if you have a function that potentially raises an exception, you could return an error code instead of a value. But that breaks a lot of type systems. A third thing you could do is call an error handler function. On error, that's pretty common in JavaScript. But you quickly end up in callback hell, so it's not so great either. Then what you could also do is return a dummy but legal value from a function but set a global error somewhere else, like a global error stack. But the result of that is potentially a lot of coupling in your code, because every part of your application needs to access that error stack. Final thing you could do is return a legal value but also set an error flag as a function result. That's called deferred error handling. It's how the Go language works. That's probably a close contender for least bad error handling solution next to exceptions. It does make your code look slightly more verbose, and you're actually forced to address any errors because they are function results. And that helps with stability. But it doesn't always lead to more readable code. And there's less room for just a quick and dirty script. But perhaps that's not a bad thing. I hope you enjoyed this video. Let us know in the comments below what your tips are for handling errors. Also, check out the Discord server for more in-depth discussions about software design and development. Thanks for watching, take care, and see you next time.